of one of the three techniques that you should be proficient at. And this is using the canceling out technique. So I'm expecting you guys to either show this is indeterminate or is, if it actually has a number, then you're just done. And there are cases where that happens on the test. You don't actually have to do anything except plug the numbers into the equation and recognize that the limit exists and it is equal to the value of the function. So if I plug in, I'm not really, I probably shouldn't put an equal sign because it's going to end up being indeterminate. So what I'm really doing is just evaluating the term to see whether it's determinate or indeterminate. So if I were to plug in the numbers and do the calculations, so 4 squared, 16, you can see I'm going to get 0 divided by 0. So that's the first thing you want to do. It's indeterminate. If I got no number here, you're done. Now, when it's indeterminate, it means these quadratic equations can be factored with the same common factor, and we already know what the common factor is because that's what makes it indeterminate. So the corresponding factor to x equals 4 is x minus 4, and you can put that in both the numerator and the denominator. And what we need to do is figure out what the other two parts are. So this is the indeterminate part. These are the determinate parts. So you go up here and you say, okay, two numbers multiplied together equal negative 12. Well, positive 3 is our only choice. And then you can just double check. If you do FOIL, you get x squared minus 4x plus 3x, which is negative 1x, and then negative 4 times 3. And likewise here, what number multiplied by negative 4, this factor is equal to negative 4? Well, just positive 1. And again, you can do the calculations and you'll see that it matches up. Okay, so then this is the canceling out technique. So once you have simplified, then you just have to plug the x value in that you're taking the limit towards. And so I get this fraction of 7/10, and that's the answer, putting a box around it. Okay. So there's a couple like that. Same procedure. There'll be probably one where you just plug the number and you get an answer. Okay. The second kind of indeterminacy is where you have a square root. So let me just give you an example. And these are actually from last year's test. I have modified these for this year's test, but it's pretty much the same deal. Okay, again, you're going to just evaluate this thing. So why don't we do that separately? So if I put this separately and I just plug in x equals 2, which is this number here. And you see this one is also indeterminate, but because it's a involves a square root instead of a polynomial, we have to use rationalization. So I'm going to do the rationalization part separately. And once it's simplified, I'll plug it back in. So I'll put parentheses around the part that involves the rational, the square root part. And then you make this longer, and then you multiply by the numerator, except that the negative part becomes positive part. If it's a positive part, it becomes a negative part. So, if I had plus 3, which actually would be, I really couldn't do that because this has got to be positive. But let's say I had 3 minus this thing, then I could theoretically, I guess, maybe not. I guess this has to be a negative sign. Anyway, so these are the same, except this is negative, this is positive, and then you multiply it by the same thing in the numerator and the denominator, and you get the right thing to multiply by. Okay. So then you multiply this thing out. So FOIL says you take this times that, so that's f, and the square root of x plus 7 times the square root of x plus 7 is just x plus 7. The inner and outer cancel out because that's why you chose that. And then you have negative 3 times positive 3, which is 9. And the denominator stays the same as the previous step. So you simplified the numerator. I want you to show all these steps, so don't leave things out here. Assume I know what you're doing, because you might just be copying stuff down, not understanding it. So this expression is the same as this expression. Exactly, okay, because it's going to still be indeterminate. If I stick in x equals 2, then I get 0 over 0 still. But the next part is to do the simplification where you cancel out that common factor, which again we knew what that was because that's what made that thing indeterminate in the first place. So once we made that simplification, then we can go ahead and write it out again. So the limit is x approaches 2 log 1 over the square root of x plus 7 plus 3. If I were to plot this function and plot this function, it would look exactly the same on the graphing utility, because you really can't see this indeterminacy on the graphing function because this is only one point involved and one point has no dimensions. So they look exactly the same. And that's why evaluating this simplified function at x equals 2 is going to give you the limit, because you're going here from one side and here from the other side, and the only difference is that one has a hole and one doesn't have a hole. Okay, so now we plug it in, and it turns out to be 1/6 again. I think I made it, I'm pretty sure I made it so it wasn't 1/6 is the answer. Okay, so we stick 2 in there. So that's 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1/6. Okay, so there's a couple of those on there. Again, some may, I'm not going to tell you one way or the other, some may or may not result in indeterminacy. List the 3 requirements for continuity. I'm not going to list them here. You're going to have to look up in your notes or in your book. But you just write it down in your paper. And hopefully we've said it enough times, you've seen enough times that we don't have to actually memorize the thing. Okay, let's talk. There are a couple of one-sided limit problems, actually. There are 3 one-sided limit problems. And again, the first thing you do with one-sided limits is you just plug the number in to see what happens. Because the 3 things that can happen with one-sided limits is you get a number, so that's one option, and you're done. Indeterminacy, indeterminate, and this you just treat the same way. Third way is this divide by 0, so a divided by 0. It's a particle asymptote. Now there is the one special case here, indeterminacy, which is the absolute value thing, where you have x minus absolute value of x minus c over x minus c, or x plus c. And that one, it has look at your sheet. So, okay, so let's talk about the third kind, vertical asymptote. So, if you plug it in and you don't get a number or you don't get an indeterminacy, how do you deal with that? So, I'm going to do one example, but we did that in class, and so we got really any practice at that, hopefully. So let's go ahead and plug the number in again and see what happens. So you get negative 3 squared plus 7 times negative 3 plus 12 divided by negative 3 squared plus a negative 3 minus 6. So the numerator is 9 minus 21 plus 12, which is actually 0. And the denominator is 0. So you might have, I didn't forget, actually, that's not a one-sided limit problem. That's another, so there's another example for you. It's not the one that's on the test, but it's another example of indeterminacy. So sorry about that. There's actually just 2 one-sided limit problems on the test. Okay, so let's go back here, regroup. Okay, so here we go. This one I'm pretty sure is. Okay, so here's the limit question. So plug the number in. So you plug -1 in. This negative is just telling you which side it's coming from. So we'll do that. So you get -1 minus 2 in the numerator. And you get -1 squared minus 3 times -1 minus 4. And so the numerator is -3, and the denominator turns out to be 0, because you'll get 1 plus 4 plus 3 minus 4. So 1 plus 3 minus 4. This is positive because you have 2 negatives. This is positive because you're squaring it. Oh, so it is 0. Okay, so there you go. So that's the third kind. So once you do that, then you have to look at which direction you're coming from. So this is from the negative side of -1. So what you're going to do is you're going to look at the signs of each one of these, and it's best to factor it now. So before we actually determine whether it's going to be positive or negative infinity, we'll factor it, which you should be able to do. So this is x. Well, we know -1 is, or positive 1 is 1 because it's the opposite of that. X equals -1. Same if it's a factor, x plus 1. Okay, so the other part is going to be x minus 4. Okay, so you can see when x equals -1, this goes to 0. This is non-zero, this is non-zero, so you end up with this result. So the only one that we have to worry about, think too hard about, is this part, because that's the part that goes to 0. So up here for the other parts, this factor and this factor is you just plug -1 in. So -1 minus 2, that's going to be negative, because you get -3. Down here you have -1 minus 4, which is -5, so it's negative. Okay, here we're on the negative side of -1, so that would be slightly more negative. So you can see if I put -1.1 in there, I'm going to have, this whole thing's going to be negative. Because I'll have -1.1 plus 1, which would be negative. So -0.1, which is negative. And you see there's 3 negatives, which is negative. So therefore, the final answer, which we'll write out. So make sure you do this. Don't just put a negative sign there. That's not sufficient. What you want to do is write out the original expression. You can show the factored version. I'll have to go back to the original unfactored. You take this negative sign, that's where you put it. Okay, so you got a couple of one-sided limits. Squeeze theorem. So squeeze theorem, there's 2 results, which says, one says the limit as x goes to 0 of the sine of x over x equals 1, and that the limit as x approaches 0 of 1 minus the cosine of x over x equals 0. So if x does not equal 0, meaning this part, plug in number. Okay, so first thing you want to do is you want to see whether the original question is applicable using the squeeze theorem. And if you're not going to 0, then they don't work. So you just have to plug in a number and hope that it isn't indeterminate. And if it is indeterminate, you may not be able to remove the indeterminacy. So, the other case is, say, we looked at this in class. So notice x goes to 0, so it does apply. And you had something like the sine of x over 4x. And what you need to do is you need to just use the squeeze theorem where it's applicable. So what I've done is I've taken this 4 and I've moved it away from the x. I mean, it's still there, it's just separate. So this thing, using the squeeze theorem, goes to 1. So you can actually break this up into 2 limits if you wanted to get real technical about it. So the limit of a product is the same as the product of the limits. And the limit of a constant is just a constant. And then the second part uses squeeze theorem, so you get 1/4. Another case would be, let's say you have, again, going to 0, so you use squeeze theorem, sine of 10x over x. Actually, let's make it over 5x just to see what we do with that. Well, the book actually says what you would do is you would define a new variable, y, which will be the argument of the trig function. And then you can solve for x. X equals y over 10. So I've just divided both sides by 10. And if you were to plug that back in to the original expression, you'd have the sine of y. And what we also do is when x equals 0, y equals 0. Okay, so if I put x equals 0 in here, it's also when y equals 0. So you're letting y go to 0, not x go to 0. So this becomes the sine of y. And for x, you put in y divided by 10. So I plug into there, you get y over 10. Again, you're going to separate so this is going to be the sine of y over, well, 5 divided by 10 is a half, so you get 1/2 y. And what we have is basically 1 divided by 1/2, this part. And then the second part is the sine of y over y. And the first number is just a constant, which turns out to be 2. You take the reciprocal of this and you multiply by the numerator. The reciprocal of 1/2 is 2, so it becomes 2. The second part is squeeze theorem, says the limit as something goes to 0 of sine of something over something is 1, so that becomes 1, and you get 2. 2 times 1 is 2. So that's the answer. The other way of thinking about this, so that's one way of looking at it. The other way that you could do it is you could just take the original expression and multiply by 2 and divide by 2. So what you'd end up with is 10x over 2. So 5 is 10 over 2. So and then you could take this, group these two together because they're the same thing. And so you can either formally define y as 10x, or you can just say the sine of something over that same something is 1. And you get the same answer. So what you end up with is this 1/2. You get 1 from the numerator and then 1/2 from the denominator. And then you have the second part here. Sine of 10x over 10x. And because these are the same, I can still use the squeeze theorem. And the limit of a constant is just that constant. And you get the answer. Okay, so those are the key things. I mean, I could give you some complicated trig identity problem, but the key thing here is that you've got to make sure that the argument of the sign is the same as what you have in the denominator. You match those two together. If you have to do a little simple algebra to make that happen, then you do. And you also have to remember that if this doesn't go to 0, you're not taking the limit to 0, then you just plug the numbers in. Okay, we talked about rational expressions, so there's a simple question about vertical asymptotes. So I'll give you a function, something like, well, here's a real simple one. So let's say I gave you this, and I said, what are the vertical asymptotes? So you would factor the denominator. And see, I got the wrong sign there. So it'd be x plus 4 and x minus 1. I knew that because this is positive 3, so I had to put positive there. So you can see I get the denominator goes to 0 under these two conditions. When this goes to 0 and that goes to 0, so we get x equals 4 and x equals 1. And those are the vertical asymptotes. So the vertical asymptotes are not 4 and 1, negative 4 and 1. They are x equals negative 4 and x equals negative 1. So make sure you put the x equals. And finally, removable discontinuities. Removable and non-removable. So, continuities. So there are basically two kinds that we have. Well, actually, there's only one type of removable discontinuity, which we've looked at, and that's holes. That's where you get 0 over 0. And non-removable, that's vertical asymptotes. So I'll give you some kind of rational function. And you'll factor both the numerator and the denominator. So I'll get x, let's see. So what two numbers multiply together give me 6. Well, 1 times 6, 3 times 2. So I'm going to use 3 times 2 because the difference between those is 1. So one's going to be 3, one's going to be 2. Because this is negative, one has to be positive, one has to be negative. Because this one's negative, the middle term is negative, the larger one has to have the negative sign, the smaller one, magnitude-wise, has to have a positive one. And you can multiply it out to check. X squared minus 3x plus 2x minus 6. And 3x minus 3x plus 2x is negative 1x, so that worked out. And then I do again. The two numbers multiplied together give me 14, 2 and 7, 14 and 1. The difference between 2 and 7 is 5, so that looks like a good choice. 7, 2. Again, this middle term is negative, so the negative has to go with the larger one of the two. So these are the factors. And so what you can see is that we have a hole at x equals 2 because x equals negative 2 because we have both in the numerator and the denominator. So the discontinuity is removable at x equals negative 2. We have a vertical asymptote at x equals 7. That's where the other part of the denominator goes. This is non-removable because there's nothing we can do to make a vertical asymptote continuous. And then I might ask you how you would rewrite this to remove the discontinuity. So what you would say is f of x equals, and from negative infinity to wherever the removable discontinuity is, which would be negative 2. Move this over a little bit, give you some space. You would say f of x equals the original function. Again, you could show, I guess, it either in factored form or non-factored form. At x equals 2, f of x equals something. So what is that something? Well, it has to be whatever the limit is. So let me go ahead and add a page. So I don't specifically ask for it, but if I said, what is the limit as x approaches negative 2 of this original expression? Okay, so I can, since I'm doing limits, I can cancel that out, and then I can just plug in negative 2. So I get negative 2 minus 3, which is negative 5, negative 2 minus 7, which is negative 9. The negatives cancel out. I get 5 9. So that is my limit, and therefore that's my value of the function. Now, in reality, what we'd have to do to make this completely correct is where the vertical asymptote exists, we wouldn't include that. So what we're doing here, because we don't set it equal to 7, might be a little more compact way of putting this thing together. Okay, so there we go. So from negative infinity to negative 2, it's just this original function. At x equals 2 is the limit of the function, which we use the canceling technique to do that. From negative, this should be from 2. From negative 2, this should be negative 2, sorry. So from negative 2 to positive 7, which is where the vertical asymptote is, it's this. So what we're saying is f of x does not exist at x equals 7. That's kind of why we're doing this here. It does the original function did not exist at x equals negative 2 either. But what we're doing is we're creating a new function that removes that discontinuity by evaluating the function at x equals negative 2. We only go up to 7 and past 7, jump over 7, because at x equals 7, we divide by 0 with a non-zero numerator, and therefore you end up with the function not existing at x equals 7. That's implicit within this definition. Because if I just said the function was this from negative 2 to positive infinity, that's not exactly true. It's positive 7, it does not exist. Okay, so you may have to watch that again just to understand the nuances, but let me tell you what we did here. So there are two kinds of discontinuities. There are removable discontinuities, which are when the function is indeterminate and the limit exists, but the function does not exist. There are non-removable discontinuities, which are vertical asymptotes. So you take the original rational function, you factor it, you find that the removable discontinuity is where the x value where you have the numerator and the denominator both go to 0. And that's what we call that a hole. So the removable discontinuity is here at x equals negative 2. Whereas the non-removable discontinuity is where this goes to 0 without the numerator going to 0. You have vertical asymptote. So we'll come back to that, but I think I skipped over something here. Yeah, the vertical asymptote is x equals 7, which is non-removable. So to create a function that removes this discontinuity, x equals -2, you find the limit as x approaches -2 of this original function, which allows you to cancel these out, and you're just left with these two terms. Plug whatever this value is into here. Make sure if you get two negatives to make it into a positive. Don't just leave it as -5 over -9. And then you can redefine your function instead of being the original function with the domain such that the function does not exist at -2 or 7. At -2, we can define the value of the function to be 5/9, which is the limit. But we still jump over that discontinuity that's non-removable. Okay, so that's pretty much it.